Howdy folks, I'm Jeff. Let's talk about taking deep learning models from research to production. I am Jeff. I work at Facebook, where we developed PyTorch really as a tool to solve our problems, but we did it in the open, and now we have this great open source project that I want to share with you. And so it's a big and a complex space to understand what all can you do within deep learning and how do you get navigated. So here's my idea of a map to how we can get started in this conversation. I really want to be focused on your productivity as a developer, and I'm going to presume that some of you have never used PyTorch before and have possibly never used a deep learning framework or done machine learning before. But I really want to dive into what are the tools and parts of an ecosystem that you can take advantage of to help you be productive. And I really want to focus on some of the concerns that a mature software engineer with relevant experience is going to have. And so here's my map to what we're going to do. Really the theme here is around that journey from research mode all the way out to production. And I'll talk about what exactly I mean by that a little bit later. All right. So to begin, I want to just give a brief introduction to why we at Facebook invest in AI. You can see it all over our products, whether or not you recognize it as AI or not. These are things like translation, which help you connect with people who you don't share a language with. Some of our AR effects and Spark AR, our ability to build computer vision models for virtual reality and Oculus products, and all sorts of other ways in which we use different forms of AI technology. And the example there from blood donations is a social good initiative that is powered by natural language understanding technology. So to do that, we need to invest in some technology that really can handle our scale. So our AI platform runs over 400 trillion predictions a day, and that number is climbing rapidly. Which means that it's also deployed on over 1 billion phones around the world. And so this is every time a neural network on your device is using part of our technology to perform a prediction operation. So what's the technology underneath that? Well, that's PyTorch. So if you've not encountered PyTorch before, I want to be a little bit more specific about who we are and what our opinions are, and really the places we invest in building technology to make you productive. I want to start with eager and graph-based execution. So this has to deal with how you as a user write your code. And so eager mode means Python as you would normally write it, returning back a result just as soon as you invoke a function. And I'll show you a little bit more about some of our investment in graph-based execution as a project and how that works for you and what that workflow looks like. Historically, we've had a lot of innovative techniques come out of work done in PyTorch due to our ability to support dynamic neural networks, by which I mean neural networks which contain control flow, if statements, that are defined by you in regular Python. Also, one of the reasons why you might want to use a deep learning framework to implement your solution to a particular technology is that you need to operate over a distributed system. You need a cluster of machines somewhere. And so we have a very powerful distributed training library called C10D that can handle doing really awesome stuff across clusters of GPU-enabled servers. Other things you might need out of a deep learning framework include hardware-accelerated inference. And so this means when you're performing a prediction in real time, depending on what you're trying to do, you may really care about taking the best advantage of the CPU or GPU underlying your program. And doing that really well involves a lot of open collaboration between organizations like Facebook, Intel, NVIDIA, and so forth. And finally, just to ground you in how we think about how we write software within the PyTorch project, we really prefer simplicity over complexity. We want you to be able to do things in writing your code what you were already naturally going to do. So write Python as you would write Python, look like NumPy when you're doing something that you would otherwise be doing in NumPy, and be very modular and opt in. Okay, so getting a little bit more concrete, what are some of those pieces when we start to look at PyTorch at a developer level? Oops, sorry, I'm going to go back. If I can figure out how to go back. There we go. And OK. Sorry, there we go. So this is just a little bit of a high-level map to some of the pieces you might use within the PyTorch library. Most people start within PyTorch because they're interested in solving some problem with deep learning. And so that's where all of our neural network capabilities in the NM module come into play. I'm going to spend a lot of time today talking about our JIT. It's called TorchScript. And this is really one of our major investments in terms of our engineering focused in building a path from research to production. There's a lot more built into PyTorch, whether it's within the core or within other libraries and in the ecosystem, and you can see some of them there. And I'll talk a bit more about some of them later. But it's designed to be a very big toolbox to support a broad range of things. I want to get some code up, though, just to give you a feel for what does PyTorch code look like. If you've not done deep learning before, I'm going to be fairly quick in just showing what are the basics of the code. So first, we need to define what is a neural network. Here, using the NN module. This gets us started right out of the gate. We need to initiate our module. We're defining a forward pass, so that is the computation we want to do in our inference operation. Here you can see the use of some pre-built layers, ReLU, dropout, sigmoid, and so forth. Showing different parts of how you work with data, some more out-of-the-box functionality here. You can see a data loader here, which is an abstraction which allows you to manage various data sets. And you can see a pre-built data set being brought in from our Torch Vision package, which is built to serve computer vision use cases, in this case, MNIST. And you can see an optimizer as well, stochastic gradient descent, all of those library standard functionality. And then here's the training loop. And so what we're going to do is we're going to iterate over each of our instances. And then you can see the steps that we have to go out there. So we're going to have to zero out our gradients. We're going to apply the forward pass within our neural network. We're going to apply our loss function, call backwards on that, and then move forward in our optimization. And then you can see some checkpointing functionality there with torch.save. It's a really simple high-level example of kind of common neural network code. Not a lot of PyTorch specifics here. I'll show a little bit more of a in-depth view of what the specifics of how you work with PyTorch are in an example a little bit later. But I want to frame that example within the context of the journey from research to production. And so if you're not experienced within the field of machine learning, parts of this workflow may not be something that you've seen in quite this variant before, but if you do have experience in building ML projects and products, you will recognize a lot of the commonalities to what I want to show here. And so this is a very high-level view of how do we take something from an idea all the way out to a real use case. So first, that we would start off with some high-level plan, right? We're going to determine our approach to a given problem we're trying to solve with deep learning. Our next and sometimes hardest problem is preparing the data. This is where it's nice to have at least like pre-built data to get started if you're trying to establish a technique or a data loader to manage existing data that you may have. And then we're going to do the part that everyone thinks about when they think about machine learning, deep learning in general. So that's build and train a model. So that's that example code I showed just previously. And that's an important step. But this next step is one that people don't often talk about a lot, and this is transferring a model out to production. So just because we've trained a model, all we have right now is an object in memory, maybe an artifact on disk. There's some additional step that we need to take to be able to publish that out, to get it out into the real world of production, because we need to deploy this in some live mode and be able to scale it, whatever that means for your application. High-level conceptual view, common of a lot of ML workflows, and what I want to call out is that 4 steps really a very difficult one, and that's very much been our experience inside Facebook AI. We've seen a ton of pain in trying to build a tool chain that it supports a productive workflow to go from beginning to end, getting stuck at that transferring from model to production. And so we want to do everything we can to remove that step by creating an end-to-end tool chain that supports being able to author a model in the same framework that you can then deploy it out to production. I want to be more concrete about what I mean by production. And so we as a project think of production in a couple of these properties here. One of them is hardware efficiency. There's some very non-trivial aspects of getting truly state-of-the-art performance on CPUs, GPUs, domain-specific architectures like TPUs and ASICs. Scalability, and so this is really being able to run across a whole cluster and being able to operate at extremely high throughput rates. There's some really fun and hard engineering problems here as well. Platform constraints. So we want to deploy neural networks to more than 1 billion phones. We also want to deploy them to state-of-the-art servers. And so there are different challenges there. And if your production spans both of those things, neural networks running at massive scale on a server, as well as running on tiny devices, then you need a toolchain that supports those things. Finally, reliability, and this gets into the scalability and reliability component here. Large-scale machine learning is an extraordinarily compute-intensive job. It involves potentially thousands of GPUs operating at the same time, which has real-world cost in terms of energy and in terms of spend for your organization. And so these are the things we think about when building out our production toolchain. So I want to talk about one piece of that production toolchain, and that's TorchScript, or torch.jit. And so what we want to do with TorchScript is to be able to power your transition from going from research to production. We want you to be able to experiment and then extract out TorchScript from your Python program, which can then be optimized and deployed to production. I'm going to show you a fairly detailed working code here. But the key point here is this is about extracting out that information from code you author yourself, not adapting your programming model to fit ours. So what this looks like is in what we call eager mode. This is PyTorch as it has always been, immediately returning out results as you would do in a normal Python program. You can prototype, you can train your model, you can run these experiments, and then you have these two paths to make this transition out to script mode. And so one way that I'm going to show you is to use the script annotation there. You also have the ability to trace. They have sort of different properties, and the only way to work through it is just to have a live code example. So we'll do that next. And we're going to do that on Colab. A quick call out to Colab. Colab is a service provided by Google Cloud. We in the PyTorch project have collaborated with that team to bring the best of PyTorch to Google Cloud on Colab. And so I'm going to show you that live in a browser window right now. Give me 1 second to mirror. Okay, so let us maybe get a bit bigger. Does that bigger sound good? All right, maybe get, yeah, bigger. Okay, so this is Colab if you've never seen it. It's a hosted notebook-like service provided by Google Cloud. It gives you free access to CPUs, GPUs, and TPUs. I just hit connect. I'm going to hang out the cloud. It's going to initialize, and you can see it's allocated me a server. And I have the ability to choose the different properties there. I'm going to go ahead and run all of this code here live. You can see none of it's been executed yet, but I'm just going to run it all to speed our walkthrough of what this code is. So one of the great parts of working with the Google team on this is this just has this incredible impact on your ability to get started. You can import Torch right away in an environment that supports it, out of the box running the latest version of PyTorch and get started. And so that succeeded. So we just import Torch. And so let's get started learning about TorchScript and the path to production. All right. So here's a very simple example of a cell. So that what we're using here is the NM module capabilities, and we are defining a simple initialization function, and we're going to define what is our forward pass, in this case, just a simple tanh. And so you can see the result of that. And this is the basics of what we might do here, and we're just showing our results. It looks a lot like the code I showed you before. I want to iterate on this a little bit. And so in this case, what we're going to show is, let's see. We'll use this function here. We're going to use a linear construct. A linear allows us to hierarchically compose our neural network. And again, we can do that in eager mode, step by step. We can just add in new elements to our neural architecture. Okay. Now, let's get really fun. And this is kind of the heart of the thing here. This new thing is a decision gate. And so this is conditional logic. And so we want to say, if in some cases the sum of this operation is greater than 0, we want to do one thing. Otherwise, we want to do something else. And this is where we get into your flexibility as a developer and your ability to have dynamic neural networks that do different things based on the input they see. This is a really powerful capability, and it's a foundational technique to a lot of the most exciting work going on in deep learning today. So now, can we use that within our linear structure? Well, the answer is yes. Yes, we can. We're able to do that. You can see the representation that's produced here. Our linear contains this new function here. Again, fully in eager mode here, and so this is just Python as you would normally do it. That was returned to you. You were able to get that immediately. And here's a little graphic calling out why that's important. is because we're not requiring a full program to be able to do useful things like define the backward function and perform automatic differentiation. We're building that graph on the fly every time you, in eager mode, pass out a new operation of some sort, and we can compute those gradients with whatever graph we have. The technique here it goes by the name of tape-based autodiff, by which we mean we're not performing the same sort of symbolic representation that you would do in a graph mode only. In fact, we're just replaying each individual argument so that we can perform differentiation at any point. This is what powers eager mode, and this is what makes eager mode work so powerfully in your workflows. So let's talk about why we would want to jump over into TorchScript mode. So eager mode is great for being able to author models, but we want to be able to get the power of our production tool chain. So we're ready to make that transition. That's where we're at in our development workflow. Here, we can see how we can trace a model here. So this is the simplified one again. This is just my cell. It doesn't have any of that conditional logic in it. It's a simple pass-through. This could be done in a sort of eager mode, or it could be done in graph mode. And so what we've done here is you can see this call to torch.jit.trace. That's what allowed us to extract out what is the computation graph of this particular neural network by putting in a given input, seeing what the neural network did, and then recording that out as a graph using TorchScript. That works great if, in fact, you have no dynamic control flow. But what PyTorch has always promised is that you do get access to that dynamic control flow. Oh, sorry, before we get to that topic, I want to show you just briefly, what did we extract? So here's a trace cells graph. You can see the actual internal representation. This is a TorchScript IR here, the intermediate representation. It shows us what is our computation graph as the runtime understands it. It's not the most readable thing in the world in a presentation like this. So I'll show you what it looks like if we map it back out to more Pythonic code representation. And so you can see here it's pretty simple here. We can see what are the operations. We call the ADMM optimizer. You can see the 10H application. Pretty straightforward, readable Python code if you want to understand what is TorchScript extracting for your program. And it did all that without requiring you to do anything other than, say, trace it. All right. It's probably a good time to talk about why would you want to extract out TorchScript. Briefly, the things that we care about is that by extracting out that graph, we now have a language-independent representation of what is the computation you want to perform. And so we can do certain things with it, like write optimization passes that can help your performance. It also allows us to export out to deployment environments that don't have Python in them. And so it's worth showing that when we do that, our trace representation, our TorchScript extracted version, does precisely the same thing on the same inputs as your original program did. We've extracted out a new program from that, the computational graph. But you can see here from when you call my cell, you've invoked in eager mode. When you call trace cell, you're operating on the computation graph that has been extracted. Exactly the same results. So let's do the fun part, and I've been eager to get to this part. And so let's actually deal with control flow. So if we have control flow like this, and we try to perform tracing, PyTorch will do its best, but in fact, we're in a more dynamic form, so this is not going to work right. It's not going to be what we really want. So here, we can say, we've got that same control flow. We've got our decision gate function. But when we trace it, we've only traced it on a single instance, just one input. And so the trace of that is the program without the control flow. It has no ability to capture that in a pure trace because it only saw one instance. That's not what you wanted, and so your code has dropped out. And that's why we provide you with yet more powerful tools than simple tracing. What are those more powerful tools? That's the script method you can see here. So here's what I've had to change to my code. There we go, just that. So by doing that, we can say that this is actually something that needs to be scripted, that we're not going to use pure tracing, that we actually want to use script mode here. And so what that script mode does is it tells the TorchScript JIT compiler to extract out what is this part of our computation graph. Don't just trace it. but actually understand what it is, map it to TorchScript, and give me the fuller representation of that computation graph. And if you can see there, we have new code extracted as a result there. And so that's this if statement here. You can read it in if Boolean, and so forth, and down in this section here. We have accurately mapped from our representation in plain Python out to a computation graph, which can take advantage of all of those optimized static graph components, which are built for production mode. And as we can see, it works just the same way, whether it's been run in eager mode or extracted via TorchScript. So that is, at a code level, what that transition from research to production looks like using the power of TorchScript. OK. Back up to some slides. And continue our journey. And OK. All right. And something that may not be obvious about seeing that at a code level is this is a really powerful breakthrough for folks who have had to live in this research and production divide for a long time, which matches my personal experience and the experience of Facebook AI. That code that you just saw allows you to operate within a shared code base for a given domain on top of a common technology so that a research team and a production team can be using the exact same tools and have a path from research to production. This is really important for us at Facebook because we often have really deep research things going on within Facebook AI Research, our fundamental research function, that needs to be connected up to the ways in which we deploy PyTorch models to production at scale and take advantage of all those capabilities we have. Here's a concrete example of that. This is the PyText library. And so this was developed at Facebook, really focused on natural language understanding and some of the specific problems of working with text. It has, we've done some great work in being able to use the technology coming out of research and putting it into production with PyText. It has really real-world production requirements. So some of those are it needs to operate in real time. A common use case of this library is that we're going to be performing recommendation predictions inside a Messenger session, inside Facebook Messenger. It needs to scale. Messenger operates in hundreds of languages. That takes that many models. It needs to operate around the world on billions of devices, and so forth. And so there's a lot of complexity to the end-to-end picture of that. I want to put that in an architecture diagram of sort of like the workflow of what that looks like. So in research mode, we need to be constantly finding new ideas, running experiments, and developing new techniques which require this great flexibility. That flexibility is great, and at some point we need to evaluate out those things, maybe sweep through some parameters, but then we probably have something we want to put to use on some level. That allows us to, so we're going to export a PyTorch model at that point. We're just going to do this in eager mode. We're going to stay in Python land. We're going to deploy to a simple Python service, which allows us to get a little bit of small-scale production metrics. This isn't a full production deployment. This is for us to feel comfortable that things are in good shape. When we do feel like we have found a successful new technique, we can now make that step that allows us to deploy from research to production. Again, still using the exact same tool chain by just doing the same sorts of steps we just saw. By exporting to TorchScript, that allows us to take those follow-on steps with that optimized model. That Python TorchScript model, that PyTorch TorchScript model is now exported in a Python-free way so that it can be used inside of our highly optimized massive scale C++ inference service that can serve billions of people. And so folks who are working on both ends of this problem are within the exact same code base and using the same tool chain. I've shown you some fair bit of specifics around how we used PyTorch at Facebook. I want to show you just a glimpse into the larger PyTorch community. A couple of production examples here. The first one is from Genentech. And Genentech's really working on a pretty important problem, which is personalized cancer therapy. The biology of cancer is such that each individual cancer is unique. Your body's response to it is going to be unique. And there's a lot of deep data problems in there that they're attacking with AI. And the approach that they're working on is that they want to leverage your own immune system using AI built in PyTorch to fight cancer. And so specifically, they're doing things like identifying peptides which can be bound to be exposed some part of a molecule that looks like the specific cancer within your body out to your own immune system to teach your immune system how to fight against it, a sort of personalized cancer vaccine. And they've seen some great results. Moving on to a very production-oriented example, I want to talk about Toyota. And so within their research group, Toyota Research Institute, they've been able to have this really amazing journey from research to production using PyTorch. So they're concerned with driver safety. More than 1 million people die in traffic accidents every year. The statistics are staggering, and Toyota is the largest car manufacturer in the world, really wants to have an impact on this. And so they're investing in technologies like autonomous driving cars. But what we can deliver today, potentially to cars, are driver-assisted technologies. So predictive driver assistance that takes advantage of some of the capabilities that we would be building inside of an autonomous car, inside a car that's driven by a human to prevent crashes. So they've been able to collect real-world examples of crashes. They've been able to map them up into a digital world. And so what we're going to see here is a crash being avoided by a car that accelerates out of the way from other drivers which are losing control of the car behind them. This is a simulation they built from real-world data. We're able to model it into this simulated world using PyTorch. But in the world of cars, when we ship to production, we don't just mean simulated worlds. We mean cars on the road. And so that, once they've validated this model, they need to then actually get cars out on the road, power them, and try to replicate the exact same examples. See if the machine learning model is able to determine that the cars behind it are about to lose control and accelerate out of the way, just using new intelligence capabilities, but nothing more than the same capabilities built into the car today to accelerate. And so a really interesting look at how we can put AI to use in driver safety. Okay, I want to talk a little bit more about the broader ecosystem. I'm going to talk about a few libraries that came out of Facebook that are focused on optimization problems. And they're both focused on techniques derived from Bayesian optimization. And so Bayesian optimization is a statistical technique distinct from deep learning. The example problem I'm going to talk about here is hyperparameter optimization. And so inside building deep learning models, there are all of these magic numbers, like the learning rate and various other hyperparameters, the number of epochs and so forth, that determine whether or not you're going to be successful in training out a model that is performant and does the right thing. They're kind of magic numbers. They're established by heuristics, previous experience, looking at someone else's paper, hoping for the best, running too many jobs. There are better ways of doing this using Bayesian statistics. And so we built out a tool chain to do that using PyTorch. All right. So first layer is the BoTorch library. So BoTorch is really around pure Bayesian optimization. It's built on PyTorch and uses some of the probabilistic modeling capabilities exposed out by GPyTorch, a Gaussian process library, also an open source. But it's really a very unframework, highly modular way of exploring techniques that allow you to perform Bayesian optimization. Moving up the stack, one of the ways in which we put that to use is our adaptive experimentation framework called AX. And so AX tries to generalize some of those concepts of how can we use Bayesian optimization techniques to develop up domain-agnostic abstractions around trying to optimize for particular goals, deploy that all out, and really make that happen very autonomously. Here's an example of what this looks like. This example is showing newsfeed ranking. And so in this case, there are all sorts of models that we want to deploy out as well as other components of data that we call a configuration. And so in sum, all these pieces of data determine what is the basis for which items should be ranked within your news feed. And we want to make changes to this all the time. We want to continually make this better. Online simulation is the gold standard for getting good labels and feedback that our machine learning model is doing well. Unfortunately, online experimentation is a scarce resource. We only have so many users working at a given time, and we don't want to expose them to untested models. And so the way that AX plays a role in this is that we can build a multitask model which unifies real live testing data from users with a much, much larger amount of offline simulation data that wasn't exposed out to real users. And it gives us an ability to understand whether or not we're accurately statistically modeling the properties of the system. And choose which new model to deploy. Both of these libraries, AX and BoTorch, are open source. We just released them about a month ago at F8. And I like to call it that they're part of a larger ecosystem, which I'm going to show you a few more examples of, that we have. And so this ecosystem in particular, this part of the ecosystem, BoTorch, PyText, our Translate platform built on FairSeek, our Horizon reinforcement learning platform, these are all things that we built to solve our own problems at Facebook. And we really want to make sure to give it back to the wider community of developers to allow you to work with these things, to use them to solve your own problems. So I want to talk just specifically about some more of those developer resources that can help you get started in becoming someone who can take models from research to production and use them to solve real-world problems. From the perspective of PyTorch and Facebook AI, we really care about the whole stack of things. We want all of these to be existing and open source. And that means everything from our open compute platform project, where we're open sourcing our data center hardware designs, all the way up to our compilers investments, where we're collaborating in open source on things like Glow and TVM, PyTorch itself, and then higher level frameworks. And as you get closer to having more specific machine learning needs, you probably care about things like pre-trained models. And we publish a lot of those. I'll show an example of that soon, and then even data sets to allow you to develop new techniques yourself, because this is part of the larger PyTorch ecosystem. And so there's a specific part of pytorch.org, the ecosystem page. I would encourage you to go directly to if you want to see what are some of the projects that you could get started with on some of the domain-specific libraries. Some of these are going to be for things like NLP. Some of these are going to be for things like vision, robotics. There's a rich community of people collaborating today in PyTorch. I want to do one more bounce across screens, and just to show you a good example of something I really like there. Okay. An example of some of the great things you'll find in the ecosystem here. So here, this is papers with code, and so this records computer science papers which develop new techniques, and then it links them up to actual implementations so that you can get started here. You can see the link here. We can go out to the PyTorch Hub for this paper. PyTorch Hub is our collection of implementations of models in PyTorch. And you can see not just the code of this thing. We can see an explanation, some of the resources. And this is all directly loadable within your own code. And so here, we can just, again, click the button, launch it up on Colab. And we can see that we have the ability with a single line of code to bring in this specific model from the PyTorch Hub. And people are adding out new models all the time. This is an open collaboration. It's not just models that are coming out of Facebook. It's all sorts of PyTorch users sharing their work and helping others be productive. I think you've heard me say a lot about developer productivity. To call out here, I've shown a few examples of some of those tooling today, but there's a lot. We work very closely with Amazon, Microsoft, and Google to make sure that your productivity as a developer who wants to have access to the best of the tools the cloud can provide support PyTorch out of the box. Things like import Torch or having it available inside of VM, having it supported within VS Code and things like that. This is a fun example of something that just launched. I want to say something like 6 weeks ago, neighborhood of. So this is called an AI platform notebook. It comes from Google Cloud. And this is a really exciting new tool chain that is a notebook-like environment connected up to the most sophisticated production deployment technologies that Google Cloud is developing. And as with my Colab example, you can just import Torch and get running. And they have examples built into it out of the box. Continuing the love, this is another collaboration we've done, again with Google. This time, this is TensorBoard, probably the state-of-the-art, everyone's favorite visualization tool for working with training deep neural networks. This is an embeddings view, visualizing an embedding space, but there's all sorts of things like learning rates and various other ways to understand what is going on inside your deep learning program. TensorBoard itself is open source, and it supports PyTorch out of the box and inside Colab as well. Part of being productive is knowing what you want to do in the first place. And so we care a lot about developer education. It's a shout out that we've been overwhelmed by the enormous growth of the community. Last year, we were the second fastest growing project in all of open source. And so we've had to think a lot about how to bring new people up to speed, and also to point to leading lights in the community and ask them to support them when they try to teach others. And so here's some examples of 2 books written by folks who are just in the PyTorch community. They're not Facebook employees, and they're really great: Natural Language Processing with PyTorch and Deep Learning with PyTorch. Both of these books are great places to start in understanding how you can solve real-world problems using the best of PyTorch technology. I think I mentioned this a little bit in the panel, but we have some great courses as well. Udacity has worked with us on a whole bunch of courses. You can see them scrolling there, all the different topics you can study in Udacity using PyTorch. And we care a lot about this. And so some of the more recent steps we've taken is we've collaborated with Andrew Trask, who's the developer of OpenMind, and PySift in the development of a privacy and AI course deployed on Udacity. And we're also funding scholarships for people to continue their studies on Udacity and learning more about deep learning. And and to call out that privacy course is in fact the library implemented in there. PySift is a PyTorch library that contains a lot of powerful techniques for working in privacy-preserving ML techniques across the range of things known within computer science. Bouncing over to another great educational partner, FastAI. FastAI is an online AI school that has just extraordinary stats around the numbers of people they reach and their global reach, and their ability to reach people all over the world and teach them the absolute latest in artificial intelligence techniques. They've just launched new courses, again in PyTorch, and they've done some great development of having easy-to-use beginner libraries that help someone become productive as a learner. And those courses and those libraries right now, the latest ones are around audio and vision, major areas of deep learning activity. So what does it mean if you walk away from this talk and want to get started? I'd point you to the Get Started page on PyTorch. Some of the ways that you can get started are to just click the button on the docs, and that will launch you out to a live Colab instance that has the code from the examples there. You can also get started in the cloud on Azure, on Amazon, on Google Cloud. And you can also install locally. Just pip install, start playing around with it on a laptop. You don't need a massive GPU-backed server to start writing code. But then once you do want to go ahead and move up to that scale, you know that you have that support there, both within the PyTorch technology itself, but also within the larger ecosystem of open source libraries and cloud partners that help you be productive in moving your models from research to production. And so that's all I really want to have to say. I just want to invite you, if you are interested in this part of open AI collaboration, I want you to join in the community. We live out here in open source. We want to talk. We want to learn more about what you're doing and understand what we could invest in and spend our time building to make you successful in taking your deep learning models from research to production. Thank you.
Thank you, Jeff, for that great introduction to PyTorch. We have about 10 minutes for Q&A. Any questions out there for Jeff?
Come on there.
Hi, Jeff. Great talk. Just wanted to ask you, you kind of use deep learning and machine learning interchangeably. Do you see any distinction between those two? And if so, what is that?
Sure, and I think that's probably just me rushing through things a little bit. And so for folks who are unfamiliar with how you would normally break down the terminology, I would say deep learning could usually be classified as a subset of all available machine learning techniques. And part of that fluidity there is PyTorch as a technology embraces more problems than simply deep learning. Deep learning is one of the ones that we work on, but we also do a lot of work within scientific computing that can sometimes use other techniques. For example, the discussion of ACTs and BoTorch, those are non-deep learning based techniques, but they are built on PyTorch. And so we work at the intersection of both.
We have a question down here, Jeff.
Sure.
Hi. For someone who has a lot of experience in Python and has a lot of interest in machine learning, but no experience with PyTorch, what would be the one definite source that you would say is, the first that someone should look at?
Kind of depends on how much time you have. So some common answers are you could do the 60-minute Blitz tutorial if you've got an hour. That's just on the PyTorch docs. If you want to commit to a deeper learning process, the Udacity and Fast AI courses are great. I also like the books as well for people who feel like they have enough grounding to be able to be productive in working through a book. I think the depth of the examples and the ability to dig deep in being able to, some of the things you can do specifically in a book are nice as well. But those would be my three main starting points, the tutorials, the courses, or the books.
Hi, just a quick question on how this platform, PyTorch, is compatible for something like edge, on the edge devices like Raspberry Pi or something. Is there like a lighter version of PyTorch?
Right, so this is, I think, a moving target within the field of deep learning in saying, how can we take something that's huge and how can we make it small and work really well? The story of what works today and that works well is really focused around mobile for us specifically. And so there are paths to take a PyTorch model and export via Onyx, which allows you access to various Onyx runtimes. I didn't talk about it in this talk, but Onyx is an open source standard collaboration that we and Microsoft and others created around the Open Neural Network Exchange format, and there's some tool chains for that. And there are particular ways, as well as there are other ways to take PyTorch models and run them on things like the Cafe to Go mobile runtime. But it's an important area. Without saying anything super specific, obviously we care and we will keep doing more stuff. This is, I think, a moving target for the whole field. Some other pieces of the PyTorch stack worth calling out, if you happen to be that specialized, if you're working, are FBGEM and QNNPAC, which are quantization libraries. Quantization is a necessary technique in shrinking down a very large deep learning model and making it possible to run either efficiently on a server or efficiently on a mobile device. And both of those are open source projects that we released last year to support the larger PyTorch ecosystem.
Something that we saw earlier today in the TensorFlow talk was that they had functionality in their new API for being able to take pre-trained published models and then use those as like input layers in your models that you make that are derived from that. And I saw that you talked about PyTorch models that Facebook provides and that other researchers provide. Like what's PyTorch's support for things like, if I wanted to use a pre-trained language classifier or image classifier and use that for some domain-specific or proprietary modeling on top of that?
Yeah, so I think this is an area that I think is emerging, that people really want something that helps with their productivity. So I think in the old days where there used to be things like just sort of static model zoos, and there was like people published up, here are some things from these papers, and they just kind of sat in a folder and no one ever did anything with them. These days, what we care about doing it within PyTorch is the PyTorch Hub. So I bounced over and showed a little bit of that. PyTorch Hub is where we would like people to share their pre-trained models and do that sort of connection up to like, where does the paper this is derived from? How does someone use this? And it's pretty easy to get started. We've collaborated with a bunch of even small startups have been able to put up their work and get it onto the hub. And it really helps with the reuse of a model because it's a single one-liner. You just call it in as it's hub.load or something like that.
Any other questions?
Hello, great talk. But I do have some machine learning projects going on, but there are more traditional machine learning things like k-means, SVN, all that kind of stuff. I don't know if I can get benefits if I port all this kind of stuff to PyTorch, or is there any can I do this kind of stuff and can I get any kind of benefit from porting k-means or SVN, all this kind of stuff?
Okay. I think I understand the question, right?
Yeah.
So if I've got an existing implementation of something that uses a non-neural network-based technique, is there any benefit to trying to work with PyTorch? I think it depends. Some of the things that I would typically be looking at are, do you have the ability to take advantage of sufficiently large data sets that you would like access to things like GPU acceleration? So we do have a portion of the community of users that I would generally group in scientific computing, working on problems that are not deep learning, and they take advantage of PyTorch as a GPU-accelerated tensor library, so NumPy on GPUs. If that sounds useful to you, then maybe we could talk and find whether or not there is a way to put that to use for your use case. It tends to be a little bit domain specific, though.
All right, anyone else? All right, I'll come to you, Brad.
I have a very short, lighthearted question. I wonder what happened to the old logo?
Sure. So you have the old logo on your stickers. So as of PyTorch 1.0, which was announced at F8 of 2018 and then delivered at PyTorch DevCon of 2018, PyTorch 1.0 now reflects the union of the PyTorch technology, the Onyx technology, and the Caffe2 technology. And so all of those are Caffe2, briefly for anyone who's unfamiliar with it, is a deep learning framework developed at Facebook, also an open source, and deployed to production inside Facebook. We chose to unify those really to achieve that research to production story of being able to have all those broad capabilities. When we did that, we created the slightly more futuristic logo that you see now.
So I just wanted to ask the opposite question of the talk that was on TensorFlow. So why would someone use PyTorch over TensorFlow?
So I did have a slide where I try to be fairly specific about our philosophies as a project, and so I'll speak in a largely affirmative mode. I wanted to paint a picture for someone who wants to take something end to end. And if that sounds like the sort of journey that you want to do and the ways in which you want to do it, there's a very specific approach at the code level, which is why I try to make that as clear as possible around how little you need to adapt your programming model to match the capabilities we're trying to provide out to you. So if you take a look at the tutorials, you open them up, you start running things, and that is the way in which you want to work, we would love to collaborate with you on that. We want to support people who appreciate this sort of flexible and highly modular approach that allows you to opt into the pieces that you care about. But I've got nothing bad to say about TensorFlow at all. They're great guys as well. I appreciated Brad's talk. It was very worthwhile.
We have time for one more question. Anyone? All right, let's give it up for Brad. Thank you, Brad.
Thank you.